Thursday, we began talking about nuclear reactions, and we talked about the idea that the nucleus of an atom is a very energetic place. And Maddie, that's because protons are all there, all positively charged, they all want to repel each other. That makes it very unstable, especially when you get to the point where there are too many protons to hold it all together. And then that leads us into the nuclear decay, nuclear radiation. Somehow, some way, those nuclei are going to start losing pieces, parts, and as they lose pieces, parts, they're going to lose energy, and that's the gamma radiation. Okay? One of the ways that that happens is nuclear fission. So give me the gist of nuclear fission. What are the high points? Go ahead.
Neutron hits an atom of uranium or plutonium,
Okay.
and it breaks up into other pieces and gives off energy.
Okay, so a neutron runs into an atom of uranium-235, plutonium-239, and then we break it up into two smaller atoms, a couple neutrons, and a bunch of energy, right? Where does the energy come from? Okay, go ahead. Matter, right? According to Einstein's mass energy equation, right? If you look at the mass of the reactants of a fission reaction and the mass of the products of the fission reaction, they are not the same. Some of that mass gets converted into energy because of this c² factor, right? Small amount of mass, big amount of energy, okay? But then we talked about the idea, what else is an important part of that fission reaction? Or what else is an important product of that fission reaction? The neutrons, right? Because we can start it off like this, right? One neutron runs into one uranium-235, and you end up with two of these smaller nuclei and then the three neutrons, right? But if we have more uranium, right, now each of those neutrons runs into another uranium-235 atom. They all split, and now you end up with even more neutrons. So now before, when it was just the energy of one atom being released, now we have the energy of multiple atoms being released. Okay, go ahead.
What happens if multiple neutrons run into the same uranium?
This is obviously an oversimplification of what actually is going on. It's not this pretty, you know.
Okay.
But a lot of it is, you know, we get enough of the uranium-235s that it happens enough that the energy released is enough to do what we want it to do, right? Yep. Now keep in mind, right, this fission is going to result in a loss of energy, a lower energy. This uranium-235, it would have decayed on its own anyway, and it would have released energy as it was breaking down. The fission reaction basically just sort of accelerates that process. All of that energy that it would have released over time now ends up being released all at once, and we can use it. If we don't do anything to control it, right, we get ourselves an atomic bomb. But then we also talked about that we can control that reaction in a way that it releases energy, and then we use that energy basically to do what in a nuclear reactor? How does the nuclear reactor work? We said that energy that's released, we use it to do what?
Heat water.
Heat water, right? And that heat, that water gets turned into steam, and the steam turns generator, and now we got electricity. Okay. Good there? Fission does not happen naturally out there in nature. It is something that we do artificially here on Earth in order to accelerate the process of nuclear decay. But there are some nuclear reactions, or one nuclear reaction, that does occur naturally in nature, and that one is fusion. Okay? By its name, we can probably figure out what's happening during nuclear fusion. What happens during fusion? Now we put things together. Whereas fission is taking big things and breaking it apart, fusion is taking two small things, or smaller things, and putting them together to make something bigger. In a similar fashion to fission, what we find out is that during the fusion process, there is a small amount of mass that's converted into energy. And if you convert mass into energy, how much energy do you get? A lot. If you look actually at how much energy is created during fusion, it's actually more than is created during fission. again, we take a small amount of mass and convert it into energy, right? Now, here's the problem though. So you might say, well, hey, if that's the case, why don't we do this in the nuclear power plant? Because the conditions that are required for fusion to occur don't happen naturally here on Earth. And if you take a look at the picture for fusion, you can see why. So, let's finish that up. The why part, we're going to answer here in a second. Alright, there's a picture of fusion. Over on the left-hand side are the reactants of fusion. Notice they are both labeled as hydrogen, meaning what? What labels something as hydrogen? One proton. Okay, now, this isn't the normal type of hydrogen that we find out there usually in nature. Most hydrogen that we find out there has one proton, no neutrons, and one electron. But here, because it is 2, that's telling us that the mass number is 2, meaning that it has one proton and one neutron. Down here, this hydrogen in the bottom left-hand corner, that's hydrogen because it has one proton, but it has 2 neutrons. These are isotopes of hydrogen. This one is called deuterium. This one is called tritium. Okay? Anybody ever see Spider-Man 2 with Doc Ock? Okay. What was Doc Ock's deal? What was he trying to do? We remember?
He was trying to like create another sun.
He was trying to create another sun. Do you remember what he needed to get into the sun?
No, he was like
He needed tritium. Okay. Go back and watch it. It's there. So, yeah. But anyway, what happens here is that in fusion, these two things smash together and make a bigger atom, just like it's showing you here. So, we get this hydrogen, we smash them together, and now we get a nucleus that has 2 protons. If this nucleus has 2 protons, what do we call it? Call it helium, okay, because that's helium's atomic number. Now, what's the problem? Simple, right? Not so simple, right? Here, what do we know about this nucleus and this nucleus here? It has what in it? What makes it hydrogen? One proton, right? But now we start getting into letter C on your outline, right? All protons have a what? What's common of all protons? Positive charge, right? If you have a nucleus that has 1 proton here and a nucleus that has 1 proton here, do those nuclei like being together? No, they're going to repel each other, right? But we can get them to do what we want them to do if we give them a lot of what? Energy, right? Remember, energy, the ability to do stuff. So in order for the small nuclei containing protons to form together, they need a lot of energy. And that energy comes in the form of a very, very high temperature. So this high level of energy is only achieved at high temperatures. Go ahead, Farm.
If they both have a lot of energy,
Yep.
though, won't they just want to repel each other even more?
Now, let's talk about that. Okay? That's a good question, Farm. If they both have a lot of energy, wouldn't they just want to repel each other more? When we talk about energy coming in the form of high temperature, Farm, what did we say that temperature told us about something? Motion, right? So if we get these things to a very high temperature, what are they doing? Moving really fast, right? They move so fast that when they get close to each other, they can't stop themselves from running into one another, okay? So that's where the high temperature, high energy actually works to the advantage here, okay? Because they're moving so fast that they can't help but run into one another. Okay? So, here on Earth, that temperature does not exist naturally. Fusion does not happen here on Earth, but it does happen all the time. It just happens where? Stars, right? The sun being a star, but more generally, it occurs in stars. Can we do it here on Earth? can, right? As long as we have enough energy. But the problem is that if you go here, right, the amount of energy that we have to put into these two things is more than the amount of energy that we get out of it. So, is it, make sense for us to do it? We could, it just doesn't really make sense for us to do it. So, there are people out there that look at the process of cold fusion, trying to get these things to fuse together at lower temperatures so we don't have to put as much energy into it. Okay? We haven't gotten there yet, but we're working on it. Okay? But the same thing happens though, right? Here, hydrogen comes together and forms helium, but in the process it loses some mass, and that mass gets converted into what? Energy, as shown by these very powerful lightning bolts. Okay? All right, are we good there? Now, where does that lead us? Well, like we said, this doesn't happen here on Earth, but it does happen out there in the universe. And that gets us into the life cycle of the star. Stars are basically nuclear reactions, or nuclear reactors. Really, really big nuclear reactors. How does a star start, though? As a baby. What do we call that baby? Okay. A bunch of particles floating around. We call that there a nebula. Okay? Yeah. Oh, so, show of hands, right? Have we done this before?
Yeah, got it.
Okay. So we won't spend that much time on it, but we will go through it again. Okay. So, nebula. What starts happening to that nebula?
Clouds of dust.
They become more together. Why? What causes them to come together? Nope. Attraction. Caused by? Nope.
They want to be
Gravity. Gravity. Right? Gravity exists between any two masses in the universe. Okay? Gravity exists even in space. Right? Don't think that when you see astronauts up in space that they don't have any gravity. Not true. And actually, they really don't have much less. Okay? Here. Here's why. Okay. So.
Airplane. Job window.
Pictionary.
So, airplane. Okay. So here's you inside the airplane. Okay?
Don't worry.
It's a cross section. So here's you inside the airplane. You inside the airplane is exactly the same as you here on Earth. Okay? Do you experience gravity when you are in an airplane?
Yes.
Yes, you do. Okay? That gravity pulls you this way. Do you fall?
No.
Why not? There's an airplane in the way, right? Okay. Now, if we get rid of the airplane, right? Like if you jump out of an airplane, right? What starts happening then? You fall. You start falling, right? Exactly the same as this ball. Okay. Okay. And as you fall, where do you go?
Down.
Down. You get closer and closer and closer and closer and closer to the ground until you hit the ground. Either fast or slow. Slow is generally better. Okay. Now, one thing that's true about gravity, and we'll learn this more as we go along, gravity acts on all objects exactly the same. Okay? So, I'm going to drop the book. All right? It's going to make kind of a loud noise. So just, all right. So, if I drop this ball, but I hold onto the book, right? Same thing happens as when I drop the ball and it goes to the ground, right? But if I drop both of them at the same time, right? What's going to happen to the book?
It's gonna land first.
Well, it's going to land first, yes, but it's going to start falling too, right? Okay? Here, let's do this. Ready? This wasn't really a good drop, but, okay. But the ball and the book both hit the ground at the same time because gravity acts both of them the same way. Okay? Now, if I do the same thing, but I drop them in this order, okay? All right, let's see if I can do better this time. Okay. On the way to the ground, what should we see? Will the ball get closer to the book?
Yeah.
No.
Not while they're falling, right?
Except then it's gonna bounce.
Okay. Now, once the book time I drop them to the time it hits the ground, we should see that they stay a certain distance apart, right? Ready? 3, 2, 1. Okay.
But
That was pretty good.
Where it's like a feather, if you put the feather on the bottom
No,
and the ball.
because gravity is not the only thing acting on that feather. What else is acting on that feather? Air resistance. Okay? But here, there's you in the plane, and gravity's acting on you. Is gravity acting on the plane? Yeah. So there's a force of gravity acting on that plane. But gravity is not the only force acting on that plane. There's also air resistance. But air resistance just happens to go this way, by the little flaps on the plane and stuff like that. If gravity's pulling down, but air resistance is pushing up, what doesn't happen to this plane? Does it go up or down? Okay? But, let's say I take my plane, and I do this. It's actually not bad, it just, well, okay. So now, the plane's falling. Now the plane's falling. But what else is falling? You're falling too. Okay? Guess what this is going to look like?
Everyone's smushed to the front of the plane.
Nope. They won't switch to the front of the plane. If you and the plane are falling the same, what are you going to do?
Stay the
You're
same.
going to stay like this,
Technically,
right?
shouldn't you have your seatbelt
This is what astronauts in space are doing. Okay? Astronaut is being acted on by Earth's gravity. The spaceship is being acted on by Earth's gravity. But they're being acted on exactly the same. And because of that, it looks like they are floating and that there is no gravity. That's not true. They're both being acted on by gravity, and they're actually, if you calculate how much gravity they're being acted on, it's almost exactly the same as they are on Earth. It's a little bit less, but not a whole lot. It's not that there is no gravity in space, it's just that everything is getting acted on by gravity, so everything does the same thing, and you can't tell the difference whether one's moving and one isn't. Okay? Does that make sense? So, where does that lead us? It leads us back to here. Okay? This nebula, is there gravity in space? Yes. So all of these little particles of gas and dust start coming together because gravity attracts things. Now, as I dropped this ball in this book here in the classroom, what happened to them as they fell? They stay the same as each other, but what happened to them individually? They increase in what? Speed. Kinetic energy, same thing, okay? They increase in speed, they increase in kinetic energy. Now, I only dropped this ball in this book about a meter, okay? How long did gravity have to accelerate them, to make them go faster? Not go long, right? But if I drop it from farther, like let's say I go outside and drop it from the roof, how much faster is the ball going to be going then when it gets to the ground? Faster. Let's say you've got two little specks of dust, and they're separated by 8 million meters. Are they going to attract each other? Yes. Real slowly at first, but as they attract each other more and more and more and more, what do they start doing? Faster, 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 faster. Until, right, they run into each other. When they run into each other, what do? That's when nuclear fusion starts. Okay? If we can get them going fast enough. If there's enough mass there, if there's enough gravity to pull those things together, and it pulls those things together fast enough that when the atoms run into each other, they stick together, now we get fusion. So, to your outline, right? Nebula. Big ball of gas and dust spread out over a big region of space. Gravity starts pulling that dust and gas together into a big dense cloud. At this point, here's where this is the determining factor. Okay? That temperature begins to rise because we've put all these things together. Gravity has been pulling them together for a really, really, really long time. Now they're going fast. If they're going fast, that's a high temperature. If we get them going fast enough, say happens during fusion? You bring two things and you put them together, right? Make something bigger. What happens when you make those two things bigger? You also get energy, right? Energy is released. If more energy is released, what's going to happen to the temperature? More energy is released, right? Those things are going to also pick up energy from other fusion and stuff like that. The temperature is going to increase. But what starts happening to things with an increased temperature? How big do they get? They expand, right? So gravity is trying to pull them together. The heat from fusion is trying to expand them out. If there's enough mass, we balance out that outward push from fusion and the inward pull from gravity, and we get ourselves a star. If there isn't a nice balance, we get something else, like Jupiter. Not a black hole. Like
That was just a joke, guys.
like Jupiter, okay? Jupiter is a big ball of gas. It is a huge planet. But in this grand scheme of things, if you look at how big Jupiter is compared to the sun, really, really, really small. Jupiter started off just the same way the sun did. It starts off as a big nebula. All that stuff, clouds and gas and things like that, start pulling things together. But there wasn't enough mass there to make it all work. So you end up with a big, well, that's actually pretty good for us, because if there was another star in our solar system, we'd probably have a problem. So, that's true. So, all right, good? Okay, all right. What happens next depends on how much mass there is, okay? The mass of the star determines what kind of a star it is. And we classify those stars on something that we call the Hertzsprung-Russell diagram, or the HR diagram. Okay? Does that look good? Does that look familiar? Yeah. Right? Okay, so, real quick, right? Each of those stars on that diagram, this is a graph. Those are all ordered pairs, right? The x-axis, that one's pretty easy, right? What are we measuring on the x-axis? Temperature, right? Which equates to what? Color, right? Okay? Over here, on the y-axis, it is labeled as absolute brightness. What did we say determines how bright something is? So either the amount of light that's reflected off of it or the amount of light it gives off on its own, right? These are all giving off light on their own. Now, so the y-axis tells us how much energy is that star giving off. Now, that doesn't always equate to how bright it looks to us. What's the brightest thing we see here on Earth? The sun. Here's the sun. It's right in the middle of the graph, pretty much, right? If you look on the absolute brightness scale, how high up is the sun? About halfway. But it's the brightest thing we see in our sky because why?
It's
It's closest to us. So this isn't how bright it appears to us, it's how much energy is it given off. Okay? This row that falls from top, or that goes from top left to bottom right, we call that the main sequence. That's where stars in their lifetime start off and end up. Well, they don't end up there, but that's where they go when they're hanging out and doing their thing. Okay? And their thing is what? Fusion. Their thing is fusion, right? That's what they do. Okay? You'll notice on your Hertzsprung-Russell diagram on the left-hand side of your page, to the right of that, there is a bunch of questions. We're going to answer those questions now. Okay? So, yeah, because they're all kind of the same pattern. Well, we might not get through all of them, but. So first, where do big stars end up? So, what would you expect of a big star?
It'll be blue.
It'll be blue. What else? It'll be bright, right? So if it's blue and bright, where does that put us on this diagram? Top left. Okay? That's where your biggest stars end up. Okay? So, Keenan, We said, what color are they?
Blue.
How hot are they?
Very.
Very hot, right? You don't have to give me exact numbers when it says how hot is it. You can just say it's very hot, right? Okay. What color is it? Blue, right? And then Maddie, what else did we say? It's also very what?
Right.
It's also very bright. Okay.
They're immortal.
Now, actually, here's the key, right? They're really, really bright because how much energy are they giving off? Lots.
They don't lose.
Because they give off energy because they do what?
Lots of
Gonna die.
They do lots of fusion, right? Because they do a lot of fusion, they're bright and they're big and they're hot, but in the grand scheme of things, sorry, that was an accident. In the grand scheme of things, they do not last very long. Now, we're still talking millions and millions and millions of years, but for stars, that's not very big. These are like your one-hit wonders, right? And they are famous and they are hot while they are there, but
How much longer does our sun have?
our sun's okay. We're about 4.5 billion in, and got about 4.5 billion to go. So don't worry.
We'll die before.
Yeah, you won't be around to see the end of that. So.
Actually, that'd be cool. Maybe not something like
Yeah,
that.
not really. When we find
Yeah,
out
for us
tomorrow
to
what's gonna
engulf
happen.
by
So you know.
8 minutes. We find out tomorrow what's gonna happen.
Doesn't
Go
it,
for it.
is everyone gonna die when we sign?
Yeah.
No, we're all gonna scavenge into the sun.
Actually, we're gonna pull a
Alright.
wall. Like, doesn't it engulf the earth and like we all burn? And,
Yeah.
yeah.
Except we'll probably not be here anymore.
Oh, but skeletons.
I mean, if you look at the normal run of like a mammal species, which we are, right?
We will not die out.
Mammal species generally last between, like, if I remember correctly, between 1 and 3 million years.
No, we're too smart.
And so,
I don't see it.
we'll be gone.
We'll probably kill ourselves.
as
There'll be
humans.
like another world war.
There'll be something else.
Aliens.
All right. So next question. Right. Next question.
Gotta go up.
Where are the stars with medium masses located?
I bet in the middle.
Right in the middle. Right. Okay. That's where our sun is. Look at our sun. So sickeningly average. Right. So, it's real important to us, but in the big picture, right? So first, how hot are they? Not very hot, right? So that means color-wise, they tend up to be yellowish, you know. Okay. But the trade-off being, right? Okay, they're going to live a lot longer. They're not as bright, which means they're not doing as much fusion. So even though they're not as big, the rate at which they go through their hydrogen isn't as great. Okay, so you can probably follow the pattern, right? Where do your low mass stars end up? Bottom right. Stars with solid masses produce cool stars that don't give off much energy. So what color are they? Reddish. Okay. They're not real hot, but the trade-off being they'll live really, really long, right? Because of the fact that they're not doing much fusion, they're not giving off that much energy, they don't burn through their hydrogen that fast. So one last correlation, right? If we go back to the electromagnetic spectrum, and especially visible light, right? Visible light runs Roy G. Biv. Okay? What kind of frequency does red light have? Low or high? Low frequency, meaning that how much energy does red light have? Right? Where does it end up on the absolute brightness scale? Not very much, right? But your blue stuff, right? Because there's so much fusion going on, and because, right, it's giving off a whole bunch of energy, blue ends up in a high energy situation, right? Just like it's high frequency. AKA purple. Or violets, depending on who you talk to.
Yeah.
Alright, are we good with that? As far as birth of a star? So biggest thing, right? Mass, how much mass does it have? Okay. We will continue on to how it's all going to end tomorrow. This is a good stopping point for us. So we'll stop here. Okay.